This is the fourth lecture in Signals and Systems, and the title of the lecture is Characterization of Systems. We had the previous day already started a brief discussion on systems, and to recapitulate what we did, a system basically is an interconnection of components, a meaningful interconnection which takes in one or more inputs. If it is a continuous time system, it takes a continuous time signal x of t and produces one or more outputs y of t. This point was not stressed earlier. If there is only one input and only one output, this is called a single input SI, single output SISO system. Single input, single output. It is not necessary that the system takes only one input. It may take more than one input. For example, if this is a weather forecasting system, then it takes wind velocity, it takes temperature, it takes pressure, it takes humidity. All these are inputs, and then the forecast says it will be cloudy, it will rain, or it shall not rain, it will be hot or it will be cold. So if x of t, if there are many x of t's, then these inputs can be put in the form of a vector, that is a single column matrix, and under that condition we shall put a bar below x of t. That means it is a vector. X of t, for example, can be a number of inputs like x1, x2 and xn of t, and this can be put in the form of a single column matrix which is called a vector. And similarly, the output may be one or more. If it is more, then we shall put a bar below it and we shall say we have outputs y1, y2. The number of outputs is not necessarily equal to the number of inputs, so we may have up to, let's say, ym of t. Then this is the output vector. So x of t produces an y of t. X of t could be a scalar, y of t could also be a scalar. If both are scalars, then we say it is an SISO system, single input, single output. On the other hand, if x of t is a vector and y of t is also a vector, then we say it is multiple input, multiple output system. All right. A system like this is a continuous time system. On the other hand, if the input is, let's say, a discrete time signal x of n and the output is a discrete time signal y of n, then we shall call this system as a discrete time system, DTS. All right. In a similar manner, x of n could also be a vector and y of n could also be a vector, and the terminologies SISO and MIMO, they are exactly similar to the case of continuous time systems. Besides continuous time systems and discrete time systems, last time we also discussed a kind of systems which takes continuous time input, produces discrete time output, and such a system is a hybrid system. The reverse can also be true, that is, the system may take a discrete time signal and may produce a continuous time signal. That is also a hybrid system, and common examples being the A to D and the D to A converter. These are two common examples of hybrid systems. Coming back to the system again, for simplicity, let's consider only SISO systems. The considerations for MIMO are exactly similar. All right. Suppose we have an input x of t and we have an output y of t. Now, what the system does is to process x of t. That is, the system operates on x of t to produce another signal y of t, which in some ways or other may be more desirable than x of t. Mathematically, Physically, of course, you have, let's say, resistors, capacitors, governors, control systems and whatnot. There can be a computer online. It could be a sulfuric acid plant which takes the raw materials and produces sulfuric acid at the output. Whatever be it, there are physical components, physical subsystems which are meaningfully interconnected to produce a desirable output. Mathematically, the system S may be thought of as a transformation. That is, x of t, the input x of t is as if transformed to another signal y of t. So, a system can also be looked upon as a transformation. And the mathematical notation for a transformation is that x of t is transformed, this is shown by an arrow, to y of t. So, any system S, the characterization, the symbolic notation for the system S in terms of mathematical symbols can be written like x of t, and it is read like x of t produces y of t. And if you want to denote the system, then you write an S here. For example, it could be one of the systems, let's say the ith system. Maybe the ith system produces y of t from x of t, then you write this system. But in the context of a discussion, if it is clear what the system is, this is usually omitted. So, we shall read x of t produces y of t. And therefore, the system S sometimes also is written as y of t is a transformation denoted by the system S of x of t. We can use this symbol, or we find it more convenient, I find it more convenient to use this symbol x of t leads to y of t. Now, one basis for classification of systems has already been discussed in the previous class. This is based on memory. Does the system possess memory, or does it not possess a memory? If it does not possess a memory, then it is called a memory-less system. And memoryless system, the other names are a static system, for example a resistor, or it's also called an instantaneous system. Instantaneous system. The definition being that the system is memoryless if its present output y of t does not depend on its past inputs. If y of t depends only on x of t, then it is called a memory-less system, whereas a memory system is one where the output depends on what the past inputs were, perhaps some past outputs also. That is, y of t is a function, some function of x of t minus, let's say, tk, and also perhaps y of t minus TL, let's say. This may be a simple way of characterizing a memory system, a continuous time memory system. That is, the function, the output at the instant t, y of t, depends on x of t minus tk. K may have a number of values, t1, t2, t3 and so on. Similarly, it may also depend on some of the past outputs, y of t minus TL, where L may have a number of values, 1, 2, 3 and so on. To understand, to appreciate what a memory system or a memory-less system is, let's take a very simple example, slightly tricky, but let's say we have a system where y of t is x of t squared. Does it have memory? No? Suppose I take y of 0.1, I take t equal to 0.1, then it is x of 0.01, which means that the output at the instant 0.1 depends, not only depends, is identical to what the past input was, input at 0.01, and therefore it is indeed a system with memory. Alright, that's why I said it's slightly tricky one. Well, you will see later that if small t is greater than 1, then y of t also depends on what the future input shall be. In other words, it is a predictor system. We'll come back to this example a little later, but you understand what a memory system is and what a memory-less system is. A memory-less system is also a static system. A memory system is sometimes called a dynamic system, and in terms of electric circuit theory, any circuit which contains an inductor or a capacitor is a dynamic system because its characterization involves differential equations, and differential equations can be solved only if the initial conditions are known. Now, what are the initial conditions? They are to be memorized by the system. Initial conditions indicate that the system has memory. In order to solve any system, any equation, if you require initial conditions, it means that the system has memory. The second type of classification that we want to discuss is invertible or non-invertible system. A system can be invertible or non-invertible. Now let's see. Yes.
In the last example, if t is bigger than 1, then the system will be future dependent.
That is correct. If t is greater than 1, the output depends on what the future input shall be. So it is.
So we can change the future input. Say I of the system, and I can do anything with the system. I can at least future is in my hand.
Future is in your hand. I wish it was true.
The positive systems, I can switch off the system, say light goes off or anything can happen.
Yeah, we shall.
How can the system be future dependent?
How can the system be future
Because
dependent?
system don't know what is the future.
Yes, that is correct. That is where the problem is. Problem of not only signals and systems but humanity in general. If they knew what will happen in future, well, we would have behaved very differently. Very differently. We shall come back to this consideration. It's a very interesting question. We shall come back to this consideration a little later. There is a class of human beings who claim that they can see the future. They are known as astrologers. Well, if you believe in them, then we'll come back to this a little later. In the context of systems classification, we'll come back to all the considerations that you have pronounced, and we shall investigate the truth or otherwise of these statements. Coming to invertible and non-invertible systems, well, it simply means that a system is invertible formally. A system is invertible if it produces from a distinct input, if it produces a distinct output. Now, by distinct I mean that if x of t is given, you can find y of t, and vice versa. That is, if the output is given, if you can find out by some transformation or by some other system x of t, then the system is called invertible. So a system S is invertible if a given xt produces y of t, and a given y of t can be used to produce x of t back, then it is invertible. As an example, suppose y of t, suppose it's a multiplier. The system simply multiplies by a constant. Suppose y of t is kx of t. All right. Then we have a system S which takes x of t, produces y of t by multiplying by k. Obviously, if I put another system which divides by k, this system S prime is such that any input it gets, it divides by k, then obviously we get x of t back. And therefore, this system S is said to be invertible system. And S prime is known as the inverse system. S prime is known as the inverse system. Is the point clear? A distinct input produces a distinct output, and from the output, the input can be recovered by a suitable inverse system. To generalize this example, a system S produces from x of t it produces an y of t. The two systems are in, what is the kind of connection? Cascade. X of t produces an output y of t, and y of t, if we can find a system, if there exists a system S prime such that when fed with y of t it produces an x of t, then X is said to be an invertible system, and S prime is known as the inverse of S. Alright? In terms of mathematical operations, matrix inversion is an example of inverse system, if you can consider that as a system. But you understand, you realize that the composite system consisting of S and S prime is simply an identity system. Isn't that right? The combination of S and S prime, because it takes X of t, it produces X of t, and therefore it is an identity system. That is, it produces an output which is identical to its input, and therefore a system will be invertible if it can be converted to an identity system by cascading another suitable system. There are many ways of looking at this. Let's take a little more complicated example and see whether that example system is invertible or not. And this example is, let's say, y of n. To bring variety into experience, we will switch back between continuous time and discrete time. Let's say y of n is x of k, summation x of k, k equals minus infinity up to the present time n. Alright? Is it a memory system or a memoryless system? Obviously it has memory, because it's the present output depends on past inputs, all the past inputs, including it depends on the present input and also all the past inputs. Now, is this an invertible system? Now, you notice, to test this, you see that if I subtract from y of n, if I subtract y of n minus 1, then what do I get? I get simply x of n. Isn't that right? Point is, can I construct a system which takes y of n as its input and y of n minus 1 as another input, two inputs now, and then produces the difference? Can I make a system? Yes, of course. You see, x of n is the input, this is my original system S, and this is y of n. So what I do is, I put y of n to an adder, and I delay y of n by one sample. That is, I call this a delay D. The system D is such that if y of n is the input, then its output is y of n minus 1. Alright. Then I subtract this. This is shown by this negative sign here. This is y of n, and this is y of n minus 1. I subtract this, and then I produce an x of n. Now, this is a perfectly realizable, it's a perfectly realizable physical system. This system is realizable, and this is obviously the inverse of S. So, this is S prime, and therefore, the system S is an invertible system. Some questions. What about this system, y of t equal to x of t? Is it invertible? Yes, it's an identity system. So what is its inverse system? Also an identity system. Alright, y of t equal to 0. Is this invertible? No, because from 0 output, you can't predict what you can't find out what the input is. Typically, it may be a circuit like this, maybe a circuit like this, and this is what you are measuring, the voltage across this, and you have an input voltage here. Well, from this measurement, from this output, you cannot guess what the input is, because whatever the input is, you shall always measure a 0 voltage. One more example. Yt equal to x squared t. Is this invertible? No, because x of t may be positive or negative. The square always makes it positive. For example, x of t equal to plus minus 2 produces y of t equal to 4. So by measuring the output 4, you don't know whether the input is plus 2 or minus 2, and therefore this system is not invertible. Any question on invertible and non-invertible? It's an extremely, there can be very extremely tricky situations where it's very difficult to say whether it is, yes.
Are all analog to digital converters non-invertible?
Are all analog to digital converters non-invertible? Well, if the sampling theorem is obeyed and the conversion is done according to the theorem, then it is invertible. That is, given the output, you can go back to the input if the sampling theorem has been obeyed.
But then you've lost some of the input in sampling.
Ah,
Part of the input.
that is the sampling theorem. Sampling theorem says that from a whole you can construct a part. That is obvious. I'm given this pen with the cap in place. I can break it up into 2 parts. It also says if the parts are given, then you can construct the whole. Obviously, if all parts are given, you can construct the whole. But suppose I don't give you the cap. Can you construct from this part only the total pen? No. Sampling theorem says it can be done. This is there in our ancient literature also. From a part you can construct the whole. We shall see in terms of sampling theorem that this is an example of that. That is, you may throw out some portions of the signal. Still, this total signal is recoverable, and that would be an invertible system. Analog digital converters are invertible conditionally. That is, whether sampling has been done according to the sampling theorem. All right, we next consider this question of future. That is a system which can predict the future. Well, the actual terminology is causal or non-causal. A system can be causal or non-causal. Mark this carefully. Causal stands for non-anticipatory. That is, a system S is causal if its present output does not depend on any future input. That is, a system S is causal if its present output y of t is determined only by what is applied to it at the present moment and what has been applied to it in the past, but not what shall be applied to it in the future. This is a causal system, and an ingenious view of the whole humanity is that humanity is a causal system. It cannot anticipate the future. Barring those a few people who are astrologers, one cannot anticipate the future. All right. Non-causal is anticipatory. Do not confuse between the two. Non-causal is a system which can anticipate its future input. If an engineer deals with systems which cannot anticipate future inputs, then why do we introduce this term at all? Well, this term is introduced due to the reason that there are indeed systems which the engineer deals with which are non-causal, and these are non-real-time systems. Let me explain what this means. A geophysicist goes to the field with seismographs, reflection or refraction or a variety of them. Or in the satellite there is a camera which takes the land picture. Now that picture is not processed immediately. That picture is sent to the Earth. There is an Earth station at Ahmedabad which receives these pictures and then processes these pictures to be able to see what the landscape looks like, where is the river, where is the mountain, and things like that. Now this processing is done in non-real time. It is not done immediately. It's stored and then at some future occasion it is processed. In this processing you know the total picture, you know the total data, and therefore any data is available to you because it's all stored, and therefore this is a non-causal system, because if you are processing for a certain value of the independent variable, you know what the inputs are for all values of independent variable, and therefore this is a for recorded data. For recorded data, any system that you use will be non-causal because you know the total picture, the total input. However, in real time all systems are causal, and therefore causal is also given the name realizable system or real-time system, and non-causal is called non-realizable. This is an easy way of remembering what is a causal and what is a non-causal system. A formal definition of causal and non-causal is like this. A system S is causal if and only if, noted by two F's, if and only if x1t equal to x2t, we'll put identical. If two inputs x1 and x2 which are identical to each other for t less than or equal to t0, alright, two inputs x1 and x2 which are identical for t less than equal to t0 implies that they could be different for t greater than t0, alright. We can have two signals like this, let's say 0, 0, and for this is t0. At t greater than t0 it may rise linearly, and at t greater than t0 it may rise exponentially. Okay, so for t less than t0 the two signals are identical, implies this double arrow, this double horizontal line and an arrow will stand for implies y1t identical to y2t for t less than equal to t0. This is the formal definition of a causal system. It says that if you have two inputs applied separately, one is x1, the other is x2, which are identical for t less than equal to t0, then for t less than equal to t0 the corresponding outputs must also be identical. They cannot be different. This is the formal definition of causality, and in testing one sometimes has to take recourse to the definition, and that's why you should remember this definition. Yes.
So if a system is time independent, so the output is time independent, what will we call it as, a causal or a non-causal?
We'll come to this. I have not come to time independence yet. Time invariance and time varying. I'll come to this classification a little later. And we'll take a system which obeys or disobeys some of the principles. But in the matter of causality, let's take an example. Suppose y of n. Suppose y of n, a discrete time system, is, let's say, 1 by L summation x of k equal to minus m to plus m, and L is equal to twice m plus 1, just for example. Is this a causal system? Is this a causal system or a non-causal system? Well, pardon me, it depends on the value of m. That is correct. For n greater than m, if you are considering n instant of time which is greater than m, then obviously all inputs are there. Xk from k equal to minus m to plus m, all inputs are there, and therefore for n greater than m the system behaves as causal. For n less than m it is non-causal. Alright, this is causal, non-causal. Now what shall you call this system? A system cannot be both. A system characterization cannot depend on other considerations. It is either causal or non-causal. It's exactly like honesty. A man is either honest or dishonest. There cannot be in between. That somebody is honest up to 1 crore and somebody else up to 10 lakhs, both are dishonest. Exactly here, a system can be either causal or non-causal. And if it is causal, then it must be causal under all circumstances, exactly like honesty. It doesn't depend on the amount of money or the temptation. If it is non-causal, it must be non-causal under all conditions. Because this causality and non-causality are conditional, the overriding consideration is this is non-causal. Is that clear? Whenever in doubt, you remember the analogy to honesty. Then you will know what the system is. The next characterization is in terms of the so-called stability. A system can be either stable or unstable. Well, this hyphen is not needed in unstable. A system can be either stable or unstable, and let's understand what stability means in the context of signals and systems. And in particular, in electrical engineering, one makes his life miserable if one encounters a system with which he wishes to perform a certain function, but the system behaves unstable. Well, it's a problem in human society also. You can't work with unstable people. The people must be stable to be able to achieve a certain objective. Now, in the context of signals and systems, a formal definition is like this. Stability is sometimes indicated by 4 letters B, I, B, O. And the meaning of these 4 letters is the following. This B stands for bounded, I for input, this B for bounded, and this O for output. And a system is said to be stable if bounded input leads to bounded output. This is the meaning of stability. That is, if the input is bounded, then the output should also be bounded, and this is the meaning of stability. If it is not so, if the output can grow indefinitely, then the system is unstable. As an example, y of t equals e to the t is an unstable system, because at t tends to infinity, y of t goes to infinity. It is not bounded. This is not correct, what I have said.
So
because t is also not bounded. That is correct. And therefore this is not a correct analogy. Alright. Let's consider another. Let's take this system. Y of n is equal to, let's say, k equal to minus infinity to n x of n. All right? X of k. That is correct. I beg your pardon. Is this stable or unstable? Well, you notice that x of k may be bounded. Let's bind x of k to a value less than equal to L. Let's limit x of k to a value less than equal to L. Even then, y of n may be infinitely large. Y of n may grow without bounds, and therefore the system is unstable. All right, this is the meaning of stability. Let's take another system. I have another example. Y of n, again a discrete time system, 1 by 2m plus 1 summation k equal to minus m to plus m, all right, x of n minus k. Is this stable or unstable? The test is that you apply an x of n minus k which is bounded and find out if the output can ever go unbounded. If it is conditional, if it remains bound conditionally, it becomes unbound under certain other conditions, then as I said, honesty or dishonesty, the system shall be termed as unstable. All right. Now, is this system unstable? Suppose I bind x of n minus k to a magnitude less than or equal to L. Then you see y of n, if it is exactly equal to L, if all samples are exactly equal to L, then y of n becomes simply equal to 1, and it can never grow in an unbounded fashion. No, not L. You see, if x of n minus k is limited to L, then I have twice m plus 1 samples of L. Yes, you are right. It goes to L, and L is bounded, and therefore this system is a stable system. What was wrong? Let's go back to our what was wrong here? Y of t is e to the t. What was wrong here? Why? What is the input? T is the independent variable. The input has not been specified, so we can't say whether the system is stable or unstable. All right, maybe the input is, let's say, u of t minus u of t minus 1, maybe a simple gate between t equal to 0 and t equal to 1. If this leads to x of t equal to this, if this leads to y of t equal to e to the t, what shall you call this system? Is it stable or unstable? Obviously unstable. If under one condition the system output grows indefinitely, that's enough to characterize the system as unstable. Is that clear? On the other hand, you may test under 100 or 1000 input conditions, and each of them leads to a bounded output. You cannot say conclusively whether the system is stable or unstable. Is this clear? Again, the same analogy. You tempt a man, let's say 1000 times with increasing amounts of money. If he remains honest, you cannot say, if he does not accept the money, you cannot say that he is honest, because 1001st attempt he might. So one cannot conclusively say whether he is honest or dishonest. It's exactly like this. On the other hand, if he accepts it once, you know he is dishonest. And therefore, for a system, if you can find an input for which the output grows in an unbounded manner, then the system is unstable. On the other hand, if you find a very large number of inputs for which the system output remains bounded, you cannot say that the system is stable. You cannot conclude, because you have not tested all possible inputs. Can you give an example of a useful unstable system? Unstable systems, there are many. Can you give an example of an useful unstable system? The oscillator that you experiment with in the laboratory. The signal generator is an unstable system, but it is unstable in such a manner that it produces a useful output, a sine wave or a cosine wave or a square pulse. A pulse generator or a signal generator is an useful unstable system, although it is not uncontrolled unstable. It is controlled. It is we who are dictating, you produce 1 kilohertz. But the system is unstable, all right. Unless we have an unstable system, we cannot generate a signal which is periodic. It goes on and on and on, and it must be unstable. Otherwise, we cannot generate. Then we come to the question of time invariance and time varying. Time invariance and time varying. Okay, a system, let me give the formal definition, then I shall explain in qualitative terms what is time invariance and time varying. A system is said to be time invariant Ti if x of t leads to y of t implies, double line and an arrow, implies that if the input is delayed by a certain amount, t0, produces an output which is also delayed by the same amount. All right? This is the test for time invariance. A system S is said to be time invariant if x of t leads to y of t implies that if the input is delayed, the output is delayed by the same amount. Now qualitatively, what does it mean? It simply means that if you do not change the shape of the input, x of t versus t, if the shape remains the same, you only shift it to the right or to the left, then the shape of the output should remain the same. The output will also be shifted by the same amount either to the right or to the left. All right? This is the qualitative meaning of time invariance, and this is what has to be tested to test whether a system is time varying or time invariant. For example, suppose you have a system which takes x of t and produces sine x of t. It's a sine generator. All right. Then if x of t is shifted by t0, that is x of t minus t0, if this is implied, obviously what the system does is it just produces a sine of whatever the input is, and therefore this will be y1 of t, the new output, and you see by comparing with 1 that this is simply y of t minus t0, and therefore the system is time invariant. On the other hand, if we take a system which is n times x of n, now if I delay the input, let's say x of n minus n0, what shall be the new output, y of n? It shall be y of n shall be equal to n times. This is not changed. This does not change because it's a property of the system. The system multiplies by n, and therefore, and this is not equal to y of n minus n0, and therefore the system is time varying. We shall consider other examples later of time varying and time invariant. The final classification on which we shall spend considerable amount of time, and this is why I relegated it to the end of the this discussion, is whether the system is linear or non-linear. And this is the only time that you shall be exposed to this concept. Most of the engineering systems that we deal with are linear systems. In practice, however, the practical situation is quite different. Most of the systems are non-linear, and we accept them or we treat them as linear because it is convenient for us to do so. Our knowledge of non-linear analysis is extremely limited, and therefore even if most practical systems are non-linear, we linearize them, we approximate them by linear systems. And therefore, it's extremely important that you understand what is a linear system and what is a non-linear system. Let me give the formal, first let me give the formal definition, then I shall explain. A system S is said to be linear if and only if it satisfies two principles. It satisfies two principles. One is if it satisfies principles of one, superposition, and two, homogeneity. Is the spelling correct, homogeneity? I think so. Superposition means, now let me explain what superposition is. Superposition means that if you have two signals, x1t and x2t, applied separately to the system, and x1 of t leads to y1 of t, x2 of t leads to y2 of t. You make two measurements, you apply two signals, one signal x1, measure the output y1, apply x2, measure the output y2. Then superposition says that if you apply both of them simultaneously, x1 and x2, and if the system obeys superposition, then the output should be the superposition of the two separate outputs. Alright? This is the principle of superposition. That is, if you get individual outputs, then if the two input signals are superimposed on each other, the output should also be superimposed on each other. This is superposition. And homogeneity says that if the input is multiplied by a constant alpha, then the output should also be multiplied by the same constant alpha. This implies a very interesting thing, that if the input is 0, then the output should also be 0. Isn't that right? Because alpha could be equal to 0. You take any non-zero input, you produce an output. If you multiply the input by 0, the output should also be equal to 0. So, homogeneity applies that 0 input should lead to 0 output. Now, this was for the purpose of explanation. We can combine the two characterizations into one. We can say a system S is linear if and only if x1, 2, you understand what this means? x1 or x2, one at a time, leads to y1, 2t. This means that x1 leads to y1 and x2 leads to y2, implies that alpha 1 x1t plus alpha 2 x2t. You see, now the input that I have constructed contains a superposition of x1 and x2 and also a multiplication by two arbitrary constants alpha 1 and alpha 2. This should lead to alpha 1 y1t plus alpha 2 y2t. If this is not obeyed, then the system is nonlinear. Alright? We'll conclude this class by taking a simple example. Let's take y of t equal to some constant m times x of t plus some constant c, which is not equal to 0. That is, we have a system which when fed with x of t produces mxt plus c as the output, where c is not equal to 0. Question is this system linear? Well, it turns out, although this is an equation to a straight line, it's a linear equation, but it doesn't represent a linear system. Why not? There's a very simple answer to this. Zero input does not lead to zero output, and therefore the system is not linear. As I said, one counter example is sufficient to disprove an assertion. 1,000 examples are not sufficient to prove an assertion. All right, one counter example is good enough, and this is one of the striking examples of a nonlinear system. Although it looks linear, it's an equation to a straight line. However, that's why I said C not equal to 0. Suppose C was equal to 0, obviously the system is linear. I conclude here.